Now we're going to talk specifically about sound waves, which are once again longitudinal or compression waves. So let's review once again some basic properties of waves. Amplitude tells us the amount of energy a wave has. Amplitude is related to the brightness of a light or the volume of a sound. Frequency is the number of waves that pass a point in a certain amount of time. Frequency, number of vibrations per second. It is related to the pitch of a sound or the color of a light. Wavelength and frequency have that inverse relationship we have spoken about, and we measure frequency in hertz. Vibrations per second, that is hertz. Vibrations per second. Once again, higher frequencies, this is once again a transverse wave, higher frequencies equal shorter wavelengths. Lower frequencies happen with longer wavelengths. Okay, so in a compression wave, the wavelength is the distance between the center of one compression to the center of the next compression, or from the center of one rarefaction to the center of the next rarefaction. Once again, wavelength is the length of the wave itself. It is a distance from one point in a wave to the exact same point in the next wave. That is wavelength. Regarding amplitude, again, brightness of light or dimness of light involves amplitude because it's the power of the wave. Loud sounds are going to have greater amplitudes than soft sounds. Bright light, greater amplitudes than dim light. The amplitude is the wave's power. How much energy is in that wave? So in a compressional wave, the amplitude is greater when the particles are squeezed together closer in that compression. The tighter the compression, the greater the energy in that wave, because it takes more energy to squeeze those particles together tightly. And then if they are squeezed together tightly, then they're going to expand or spread farther apart in the rarefaction. So a greater amplitude wave, compression wave, is going to have a tight compression and very widely spaced rarefactions. That is how you can judge visually the amplitude of a compression wave. The amplitude of a sound wave can be seen here visually, or you can hear the volume level of a sound wave, and that will also tell you the energy amount or the amplitude. So let's look at these sound waves here. Once again, a sound wave, it's a longitudinal wave or a compression wave that it's produced by variations in air pressure. So some source that is vibrating, we might think of a speaker, or you might think of a tuning fork, or slamming your fist on a desk is going to create vibrations. Those vibrations change the air pressure, and they push those molecules of the medium back and forth. Here you see one sound on top here, it's just one vibration. You see it travel all the way the length of the wave. And then on the bottom you can see multiple vibrations, sound waves traveling through a medium. And once again, these particles are just traveling back and forth in place, but the energy of the wave you can see travels. So here we can see a particle, it's just going back and forth, back and forth, back and forth, but it touches the next particle and transfers that vibration along, sending the energy of the wave the full distance. Here we go. This is a nice tight compression right here, and then you see this widely spaced rarefaction right here. So if it takes a medium for a compression wave to travel, can sound exist in a vacuum? Like in outer space, if you see a spaceship explode or whatnot, are you going to be able to hear that explosion? Of course the correct answer is no, because in a vacuum of space there is no medium for that sound wave to travel through, therefore it goes nowhere. So how do we measure sound waves? We can measure them in hertz. Once again, The amount of vibrations per second is the hertz of a sound wave. That is the frequency. We call this pitch. The faster the vibration, the higher the hertz, the higher the pitch. The lower the pitch, the slower it is vibrating. Once again, amplitude is volume when it comes to a sound wave, and we can measure that volume in something that is commonly called decibels, or dBs for short. You can look at this chart here, and as the decibels grow higher, so does the energy or the amplitude of that wave. So a whisper might be 20 decibels, whereas a bicycle horn or a firecracker, balloon popping is going to be in excess of 100, 150, even more decibels. So simple measurement system of decibels for the amplitude or for the power, the volume of sound waves. So what about the speed of a sound wave? We've talked about the speed of electromagnetic waves at 300,000 kilometers per second. Well, sound waves are clearly not as fast. Sound waves are 343 meters per second, not even kilometers. So there's a huge difference. And we talk about the speed of sound through dry air at sea level. This matters, of course, because dry air is going to be less dense than moist air, because dry air is going to have less particles in it. Therefore, that sound is going to travel a little more slowly because it's less dense. And at sea level, we can talk about the pressure. That's going to affect the density of that air as well and how fast that sound wave travels. So if there was more moist air, then it would travel faster because it would be more dense. So 343 meters, but here in the United States, what we talk about? We talk about miles per hour, right? So we can do a simple conversion here and come up with the fact that it travels at 767 miles per hour. Once again, the speed of sound changes by the type of medium, by the humidity and pressure and temperature of the air, because those particles move faster at higher temperatures, right? So that sound wave would travel faster. Absolutely. So these things are different. Multiple things affect the travel of waves. Just like other ways that we've talked about, sound waves can be reflected and refracted and diffracted. Okay, what would you call a sound wave that is reflected? That would obviously be an echo. Absolutely. Sound waves that are reflected are echoes. And they reflect in the same ways, right? A regular reflected sound wave would sound very similar to what the original sound is. However, diffuse reflection, that would cause sound waves to not travel, which would make them quieter. It might help you to soundproof something, not allow waves to travel the way that they should, causing them to not be as loud. With sound waves and other ways, we can talk about interference. Two different specific kinds of interference we talk about are constructive interference. Obviously, those are going to build on each other, right? Construction is building. Constructive interference are going to build on each other. So when the crests and the troughs line up, here you have two smaller amplitude waves. When the crests and troughs line up, you can build with that interference and you get a much larger wave. Whereas you also have destructive interference. If the crests and the troughs are opposite each other, then they're going to cancel each other out. So it's like subtraction. So constructive interference, when the crests and troughs line up, that's like addition. You're going to build a bigger wave. In destructive interference, they don't line up. They're kind of, see, this crest here is lined up with a trough. That's opposite. Crests and troughs are opposite, so it's like subtraction. So you get a much smaller wave, and sometimes it cancels all the sound out completely. Combining waves, you got constructive, once again, where you get a larger wave, and destructive, where you get a smaller wave. You're either adding or subtracting the amplitudes. That is what's happening. Now we're going to talk about a concept called the Doppler effect. Not very difficult, very simple concept. When you have a source of a wave that is not moving, we call that stationary, not moving, then all you can see as it progresses out, the wavelengths and frequencies are all the same. But with the Doppler effect, when that wave source is moving, so let's say we're standing over here, and if the wave source is moving away from us, you can see that these wavelengths are greater, therefore the frequency is lower. So it changes, and remember, frequency is responsible for how we hear the pitch of a sound. So if we're over here, then this sound is going to have a much lower pitch than it would if we are over here. Because you see here, the sound is moving towards us, the wavelengths get smaller, the frequencies get greater, so it's a higher pitched sound. So as it's coming towards us, it's a higher pitch, but then once it passes us, right, suppose we're here standing at 2. As it comes towards us, it's a higher pitch, but then once it passes us and is going away from us, it's a lower pitch. You've probably heard this when things fly overhead or a car goes past you. It sounds like it's getting higher in pitch as it comes towards you and lower in pitch as it goes away from you. We call this the Doppler effect. Pretty simple. Here's another example of the Doppler effect. We define this specifically as the shift or change in frequency caused by motion. Right? We call that the Doppler effect. And it's the same thing. Here, there's no motion, so the frequency of the sound itself does not change at all. But here, if the sound is moving towards us, we're going to hear a higher frequency. Once again, that's the same thing as a higher pitch when we're talking about sound waves. And you can see these wavelengths are shorter and the frequency is higher by person A with the moving sound source. And you can see over here, if it's moving away from us, we hear a low frequency because those wavelengths are longer, giving us a lower frequency, causing us to hear a lower pitch. So when it comes towards us, it's a higher pitch or higher frequency. If it's going away from us, it's a lower frequency and a lower pitch. And here's another thing, just as the same example with ears, because that's where we hear, right? So as the sound comes towards us, you see once again higher frequency, smaller wavelength, higher pitched. As it's moving away from ear number D, or letter D here, you get a longer wavelength, a lower frequency, therefore a lower pitch. And that covers sound waves.